I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. What this is showing is the power of what you can do when you have a normal distribution and how you can gather the information you need because of some common characteristics of a normal distribution. With homework 1, it's providing you the critical values that you need to then find out this information. And really, when you're doing this, there's some key things that you want to look for. And one is, what's the mean value of the sample statistic? And then also, what is the standard error of the sample statistic? And probably the third thing that you want to find is, what's the significance level or the range of values that you're looking for? And when you have that, you can then find out the stuff that you're most interested in. So with the commuting times, in the example, it says the mean is 21.97. So that was the mean number of minutes that people in St. Louis spend commuting. And then the standard deviation is 0.65. So you set up your normal distribution in here. And then what it's asking you is, what proportion of the commute times are greater than 23 minutes? Because you're wanting to know what's greater than, you do a right tail. And then you go down here and plug in which values are greater than 23 minutes, or what proportion of the values. It tells you that it's 0.057. The proportion of values greater than 23 minutes is 0.057. One of the reasons why we did this particular assignment was this is a very similar approach to how you do p-values. Say your significance level is 0.05. Any value that's greater than 23.039 is going to be considered significant when we do a hypothesis test. Because all of our sampling statistics will be normally distributed, we can use this type of application to quickly find out where our observed sample statistic fits on this distribution. The other one was, what proportion of values are less than 20 minutes? Can someone give an example of how we would find what proportion of values are less than 20 minutes? Would it be a left tail, two tail, or right tail? Okay, left. And then we go down here, and that's where your cut point is. So you want to know what proportion are less than 20 minutes. So in a sense, the values along the x-axis are the values of whatever it is that you're measuring. Mm-hmm. In this case, it's minutes. The values that you'll see up here is just telling you the proportion of values that are under the curve for that region. See, up until this point, we've always had a significance level of 0.05, and we kind of know it's 2 standard deviations out. But if you have different cut points, it can't exceed this amount. This allows you to sort of quickly enter that in to find the answer. The next example was with hearing loss in teenagers, and the formula for that is p hat plus or minus z star times the standard error. This is the normal distribution, and what we covered at the very end of class yesterday was a thing called the standard normal distribution. Anyone remember the parameters for a standard normal distribution? What's the mean?
Mean is 0.
Okay.
Deviation is 1.
So 0 and standard deviation is 1. The great thing about this particular distribution is wherever your point is on the curve, that is its z-score. It lets you know how many standard deviations it is away from the mean. So we have p hat, which is the sample proportion plus or minus z star times the standard error. And so we have p hat, we have standard error, and z star is basically defined by whatever your confidence interval is. In this example, the confidence interval is 90%. So two-tail, because you're wanting to know the proportion in the center. That tells you that the upper bound of the 90% confidence interval, the z-score is 1.645. That just lets you know the value for right in here. In the past, what we've typically done is a 95% confidence interval. And does anyone know what the z-star for a 95% confidence interval is? 2. We can test that by saying, okay, no, I actually want to do 95% confidence interval. The value we see is 1.96. The good thing is that you don't have to do the math of calculating it, like that's not part of the scope of this course, but you still need to find those numbers, and so this is a quick way. The other way that it's been done in the past is you'd have a big list of numbers correspond, like you'd have one page that said 90% confidence interval, and then it'd have a list of values that you would plug in, and just much more complicated. So hopefully this way of doing it is more straightforward. And as I said, I'll get you guys this website because it actually hasn't been launched, but it's ready to go, so we can use it. So for the next 4 days, just to give you a mapping of where we're going, the next 2 days is going to be inference for categorical variables. We're going to be looking at categorical variables, in particular the distribution of sample proportions, the confidence intervals for sample proportions, and then hypothesis testing with sample proportions. And so you'll see a little bit of a theme, like we're going to look at confidence intervals and hypothesis testing. And then the next day is going to be inference for categorical variables, but it's going to be for 2 proportions. So like we've been doing differences in proportions, and we're going to look at confidence intervals and hypothesis tests for differences in proportions. And then the third day is going to be for quantitative variables. And we're going to do for single quantitative variables, and then the next day will be for 2 quantitative variables. So fortunately in this, there'll be overlap. You'll be like, oh, okay, there's similarities between how you deal with proportions and how you deal with quantitative variables and means. Yeah, for the next 4 days, you're going to be seeing stuff over and over again, but in different contexts. Standard error is going to be a big focus of what we're going to be looking at, because it lets you know how much error is in your sample statistic. How confident are you in your point estimate or your sample statistic that you have? Just as a note for terminology, and I've noticed this in the book, and it's probably helpful just to be aware of this, is that when it refers to the standard error of a sample statistic, it's a shorter way of saying the standard deviation of the distribution of sample statistics. So we have our sample, and in this case it's a categorical variable, and so we have our sample proportion. That's our 1 point estimate for the population. But we know that that's just an estimate of the population, and we know if I did a different sample, it would be slightly different proportion, and if I did 1,000, you'd have a distribution of different sample proportions. And what we're interested in is how much do those sample proportions vary from sample to sample. The way that it's described is it's the standard error of your sample proportion. I'm bringing that up because I think it can be confusing, because you're like, wait, how is that different from the standard deviation of the sample proportion? Maybe someone can try. What is the difference? This will test if it's sinking in. The difference between the standard deviation of a sample proportion versus the standard error of a sample proportion. You have a sample, and I'll just use a simple example like height. The sample values of height, like the height of Duke students, the values are distributed in this way. And so you have a mean height, and then you also have the standard deviation of heights. So that would be the standard deviation of the sample mean. Let's say mean height is 64 inches, sample mean is 64, but we want to know how that sample mean varies, because this was only a sample of Duke students, and if we took another random sample of Duke students, the sample mean might be 64.2. And then if we did another random sample of Duke students, the sample mean for that would be 63.9. So you want to know how much this sample statistic varies from sample to sample. And that variation is where we get that sampling distribution. This would be 64, 65, 66. And so you put in, okay, we got one at 64, one at 64.2, one at 63.9. And so it's going to be centered around the observed sample statistic. And when you want to know how much these sample means vary from sample to sample, that's the standard deviation of this distribution, which we also call the standard error.
You still find it the same way if your distribution is different.
Yeah, the reason why they call this standard error is because then you'll often say, what's the standard error for this sample mean? They're not asking what's the standard deviation of this, they're asking what's the variation in the sample mean. So again, you'll see they'll say the standard error of the sample statistic is this, and you need to know that what they're referring to is how much does the sample statistic vary from sample to sample. That could be a thing that trips you up. So then the focus for the next 4 days is there's a way to estimate the standard error of a sample statistic without having to simulate thousands of randomization samples. Up until this point, the only way that we've been able to calculate the standard error of a sample statistic is to go do the bootstrap sampling distribution and then find out, okay, we do 1,000 samples and then we calculate the mean for each of those samples and then find out how much it varies. There's a way to estimate it. You never really know because even 1,000 isn't the whole universe of random samples you could do. You could do 10,000 or 100,000. But what we're going to focus on is a way to estimate the standard error, and in this case, of a sample proportion. The standard error of a sample proportion, this is how it can be calculated. So you could either do the bootstrap sampling distribution, or you could do a formula. And maybe at the end of the class, I'll let you guys decide which way you prefer better, of doing it sort of more tactile, like actually running through 1,000 samples, or doing it with a formula. My sense is doing it the tactile way lets you know what's going on, and then it'll at least give you confidence in the formula. What's in this formula for standard error of a sample proportion? What are the symbols that you recognize? You know what n is though, right?
Yeah, that's
Sample size.
C.
Yep. So P, anyone know what P is?
Is that portion?
Proportion of what? It's the population proportion. So the formula is the population proportion, and it also includes your sample size. Notice that the sample size in the denominator, as the sample size increases, so as you have a larger sample, the standard error will decrease. That should make sense that if I want to know the height of Duke students and I only sample 5 people and I get a sample statistic, and then I want to see how much the next sample of 5 would vary from my original. If you're only looking at 5 people, there's going to be a lot of variation in your sample statistics. Whereas if I took 500 people, the sample mean that I get is not going to vary much from sample of 500 to 500 because I will have a pretty good representation of the Duke student population. We're going to do a coin toss, and when you call what the coin is going to be, say you do it 10 times, the number of right guesses is a sample proportion. Think about flipping the coin 10 times and you guess 10 times. The sample proportion is the number of right guesses you get. When randomly guessing the outcome of a coin toss, we actually know what the population proportion is going to be. It's going to be 0.5. So we take the population parameter, which is 0.5, you multiply that by 1 minus 0.5, and then you divide it by the sample size, and in this case we tossed the coin 10 times. If we ran this experiment and tossed the coin 10 times for Tim and he guessed it, let's say he got 4 out of 10. What would our sample proportion be if he got 4 out of 10? 0.4. P hat is 0.4, and then if we want to go over here and look at, that's one sample But then if I went to McKay and I went to Rachel, we want to know how this sample proportion would vary. We know it's going to be centered around 0.5 because that's the population parameter in this case. And so we have 0.4, 0.6, and so you're going to have, and then what we're wanting to find is what's the standard deviation of these different samples. We have the standard error is 0.158. So how does this compare with the value we get via bootstrap sampling? So we're going to go back to what we've done. Does anyone remember how we would do this in bootstrap sampling?
We would go to bootstrap.
Bootstrap for what type of variable?
The one binary category.
So it's a single proportion, and then we edit our data. Our count would be, this is where we put in our population parameter. So 5 and 10 is our sample size. And then if we generate it 1,000 times, so this is sort of replicating if you did tossing the coin 10 times and you do that 1,000 times to get 1,000 of these sample statistics. You see that the mean is 0.508, which is more or less right. You're simulating it, so it's not going to be a precise number. And then the standard deviation of that distribution is 0.156. And so again, the one that we calculated using our formula was 0.158. What this is showing you is that there's two ways to arrive at the standard error of a sampling distribution. One is with the bootstrapping, which we did, where we simulate 1,000 samples, doing it 1,000 times. And with this example is how you do it with a formula. But if I just started with a formula, it would make no sense. But hopefully this will show you the connection between even what standard error is and how we arrive at it. Here's just a replication of what we did on the stat key. And then to show you how sample size affects the standard error, this is what we did do where the sample size is 10, the standard error is 0.158. If we increase the sample size to 100, the standard error goes down. And so what that means is the range of sample proportions becomes much tighter. And it makes sense because when you get up to like 100 coin tosses, you're going to basically get really close to 0.5 of them right. Calculating the standard error for a single proportion is this formula. There's a problem though. Unlike the coin toss example, we typically do not know the value for p.
Oh, so we gotta find out how to get p?
We gotta find out how to get, unless you know. Do you know p?
No, I don't know p.
Don't we never know p?
Exactly, yeah. The reason why I did the coin toss example is because that's a situation where actually p is known. But in general, in social science,
Way too easy.
the whole reason why we do statistics is because the population parameter isn't known. And that's why we do a sample of the population and then we make inferences about the population parameters. But at least you know that this formula works. We tested it in both directions and we came out with the same standard error. It's like, okay, we don't know what p is. It says that we can estimate the standard error of a sample proportion by using our best estimate of the population proportion, which is our sample proportion. When I'd ask what's the population proportion, I would say, well, what's our best estimate of what the population proportion is? And it's our sample proportion. The sample proportion, the sample that we have actually has value because it gives us a pretty good estimate of the population proportion. That's nothing new, but it's just taking something that we've done and putting it in a new context. So we know that the sample proportion is a pretty good estimate of the population proportion. It's not exactly it, but it's a good estimate. We can rewrite the formula to say that the standard error for the sample proportion, and we just replace p with p hat, changes to being is approximately equal to. So this is something that we've seen before is the X% confidence interval equals the sample statistic plus or minus Z star, and Z star corresponds with whatever confidence interval you're wanting times the standard error. So the sample statistic is p hat plus or minus Z star times, and then we put in our new formula for standard error. And again, Z star, what we used with the computer this morning, you say if it's a 90% confidence interval, then you just say, okay, what's the upper bound of the 90% confidence interval? And that's our Z value for this formula. The reason why Z is kind of in this notation is because the type of confidence interval you might be looking for will change from problem to problem. Z star is a location on the standard normal distribution, and its value is determined by the confidence level that is selected. One that we're familiar with is that a 95% confidence interval, Z star equals 2. Let's go back to a familiar example with Obama's approval rating. We remember that p hat was 0.49 and the sample size was 1,500. Does anyone remember what the 95% confidence interval was?
Plus or minus 3.
Yeah, plus or minus 3. So let's see if they were right. Our formula for 95% confidence interval is p hat Z star, and then the formula for standard error of this sample proportion. So you plug in the numbers, and keep going, and actually it's plus or minus 0.026. I think Gallup rounded up, but it basically comes out to the same thing that Gallup did. And it also, if you remember when we did the bootstrap sampling, we replicated the Gallup study 1,000 times, and we got 1,000 sample proportions, and we found out that the standard error of this distribution of sample proportions was 0.013. So that's the same as what that is right there, would be 0.013. So you can get it both ways. You can get it using the formula, or as we've done in the past with the bootstrap sampling. What's interesting is, using this, we actually didn't know the true population parameter. We didn't know what the true proportion of people who approve of Obama as president. So we did our best estimate, but our best estimate turns out to be a really good estimate. I mean, it gives us the same confidence interval. The other way, if you remember the 95% confidence interval using the percentile method, where you just look at what proportion is in the middle 95%, and then what's the lower end and what's the upper end, and that also gives you the confidence interval. This is not anything new, it's just another more general way to calculate. Like if you weren't going to do bootstrapping and you wanted to enter a formula. And the good thing is that formulas, when you guys work with the GSS, it automatically computes these things, but you need to know what it's computing so that you put in the right values. What this allows for is looking at other levels of confidence. I'll need to change these slides so that they use the new and better applet. But rather than just saying, okay, we're only looking at 95% confidence interval because that's plus or minus 2 standard deviations from the mean, you could look at a 90% confidence level would have a Z star of 1.645, a 99% confidence interval would have a Z star of 2.576. You can adjust your confidence level. So if you have a particular test where they require a 99% confidence interval, you're not stuck in saying, well, I only learned how to do 95%, so that's the best I can do. You can adjust it to vary on what you need to look at. Okay, so this is a new term. It's important because it's going to keep coming up and you're going to be like, what are they talking about? Why do they all of a sudden pop up this new term and I don't know what it's referring to? So I'm going to help you see what it's actually referring to. So test statistics. A test statistic is the observed sample statistic you use when conducting a hypothesis test. I think this has even come up on the tests and even in the homeworks. When I've been sort of hammering to you guys, like, what's the observed sample statistic? Some of you will say, you'll give me the sample size, or you'll give me men and women, or you'll say a bunch of different things that aren't accurate. The observed sample statistic is the particular statistic that you're going to be testing. Like when we do the gender and exercise, and we want to know what's the difference in the amount of time exercising between men and women, the test statistic is the difference X bar men minus X bar female. This is the statistic that we're going to be testing. It's critical that you know, because then this becomes the focus of your hypothesis test. You're going to have a value here, and I think in this example it was 3 hours, and you're going to say, how unusual of a difference is this? If in a world where there was no difference between men and women, how unusual would it be to get an outcome that's 3 hours or whatever? So whenever you see in the book that they're referring to test statistic, it's referring to the sample statistic that you're going to be focusing your research on. You're testing to see how unusual it would be to get this value by random chance if the null hypothesis was true. This is the whole framework for a hypothesis test. Just important that you know, test statistic is the critical observed sample statistic that you're wanting to see how unusual it is. And so then through the hypothesis test, you determine the probability of getting a value as extreme as your test statistic when the null hypothesis is true. This probability is the p-value for your test statistic. And then the last one is the location of the test statistic on the sampling distribution when the null hypothesis is true has a corresponding z-score, which can be used as another way to calculate the p-value. So if we wanted to know the p-value for your test statistic, and let's just say in this example, our test statistic, which you would enter right down here, is 1.5. That's your observed sample statistic for whatever it was you're measuring. Let's say it's 1.5, and we want to know the p-value. What would be the p-value of that test statistic?
0.062.
Yeah. You can bring it back to the normal distribution to then see what proportion of values are as extreme as your test statistic. Hopefully clarified test statistics, and the reason I did that is because we're going to look at a standardized test statistic. Now, this makes life simpler for you and for everyone who does research if you can have standardized values. What standardized means is you're all looking at the same measure. So if you notice, like when you go and buy shoes, there's like about 4 different numbers on your shoe size. There's like the UK version and the, I don't even know what they all are, but there's 4 different shoe sizes. And wouldn't it be nice if there was just one standard way to measure shoes? You just know around the world, my shoe size is 7, and that's just a standard thing. That's basically what they do in statistics, is they have a standardized test statistic. In this case, we're looking at difference in mean height, and our test statistic is 3 hours. Well, if we're doing another study somewhere else and it has another measure, it'd be hard to compare the two. And so what this is doing is it standardizes the values for all test statistics. So the standardized test statistic is called the Z statistic. Anytime you see Z, it usually means it's referring to standard or normal, like Z-score, Z statistic. And this is in the context of doing hypothesis tests. And so the way that you standardize your test statistic is you take your test statistic minus the null value. And so this is in the context of hypothesis test. And then you divide it by the standard error of the test statistic. Remind me, what is the test statistic? Yes. Make sure you remember that test statistic isn't some random thing that we just grabbed from somewhere, but it's your observed sample statistic. We're wanting to create a standardized value for it. The Z statistic is the number of standard errors, and observed sample statistic is from the null. Remember when we calculated Z-score for a particular value? Does anyone remember the formula for that? X minus X bar over standard deviation, and so that's Z-score. Let's say that the value for the Z-score was 1.5. What would that value tell you? If this value X has a Z-score of 1.5, what does that mean? Brittany?
How many standard deviations it is away from?
Yes, it's 1.5 standard deviations plus or minus the mean. That's Z-score. Z statistic is very similar in that you have your test statistic, which is the value that you're interested in. You want to know how much it differs from the null value. The null value is what would be the value of the test statistic if the hypothesis was true. We'll work through what null value is, but null value is what the value of the test statistic would be if the null hypothesis was true. And then you divide by the standard error of the test statistic. Let's say it gives a value of 2.5. So we have Z statistic was this. And so if we have Z statistic for our test statistic is 2.5, what is that telling us? it's 2.5 standard errors plus or minus whatever the null is. Okay, so there's a relationship between z-score and z-statistic, and you'll see why this is important or relevant. You can plug any test statistic into this to get a standardized z-statistic. And so remember, like when we did the example of ACT score and SAT score, and so we wanted to know, how do we compare a person's SAT score with another person who has an ACT score? We needed to standardize it, and the way that we had done it was we took the person's SAT score minus the mean value of all SAT scores divided by the standard deviation of SAT scores, and it gave us a z-score. And then we did the same for the ACT, and it gave a z-score of, let's say, 1.3. By standardizing it, you could compare SATs with ACTs, and you could see, oh wow, this one is 1.5 standard deviations above the mean, so it's a better score than the ACT, which was only 1.3. We're doing the same process of standardizing, but now we're doing it with our test statistic. We'll look at an example in StatKey. So this is what we've done in StatKey of the difference in means of exercise time. So if we have men's exercise time, women's exercise time, and this is the randomization sampling distribution of when the null hypothesis is true. If we wanted to find the z statistic for our test statistic for this example, what would it be? 3. How'd you get that?
It's the difference between the two.
Okay, it's right here. It's the difference. So what's our null value? 0. So we do 0. And then what's the standard error from the bootstrap? 2.31. So divided by 2.31, and it equals 1.29. So it equals 1.29. What does a z-statistic of 1.29 mean, Brittany?
It's how many standard deviations from the null. It's within it's 1.29 standard deviations away. So you can calculate what percentage that comes.
Okay, so it's 1.29 plus or minus the null. And the null is 0. So it's 1.29 standard deviations from the mean. So if we have a threshold level of 0.05, like a significance level of 0.05, and our test statistic is 1.29 standard deviations from the null value, would we reject the null hypothesis or accept it? Well, I'll show you, because this is making an extra step. But let's say, okay, right here is a right tail, and then down here is where we put our test statistic, and so it gives us a p-value of 0.098. Another way to look at it is on the standard normal distribution. We can plug in our standardized test statistic, and it's 1.29. It gives you a p-value of 0.098. The example, when it's not standardized, you plug in your test statistic 3, and then it tells you the p-value, the proportion of values that are greater than 3, and it's 0.098. But when we standardize it, and this is where it's really, really helpful, if you can standardize your test statistic, so you take 3 and you standardize it to get a z statistic, and in this case it's 1.29, then you can just go to this distribution right here, which is the standardized normal distribution, and you can plug in your standardized test statistic right here and get your p-value. You know, up until this point, we've been using the computer simulation to figure out what the p-value is, and it's like, if there's a standard way to do it, where you can take all these different test statistics out there with all these different random values and standardize them, then you can calculate the p-value using one standard measure. You can kind of compare, like if we want to know the difference in means of men and women and how unusual our observed sample statistic is compared to like the difference in the amount of sleep that men and women get. If we wanted to know which one is a more extreme difference, we could compare them, even though we're talking about hours of exercising versus hours of sleep or something. Moving forward, our test statistic will always be standardized. It's important to know how we go from the unstandardized test statistic to the standardized. And so instead of using this one that didn't work, I used the StatKey website to look it up. Both methods provide approximately the same p-value of 0.1. Yes?
How often is the null value going to be 0?
Most examples that we use is going to be 0 because you're talking about when there's no effect or no difference. I mean, I know there's examples where they say you're tossing a coin and they think the coin is a loaded coin, and so the null value ends up being 0.7 or something like. And you can tell though, because in the wording of the question, you're wanting to see, you're usually looking at difference of means or like, is there a correlation? And the null hypothesis would say there's no correlation, so null would be 0. So almost every example that we'll use, I think null is 0. Yesterday we were talking about our firstborn children smarter than later-born children. We want to calculate the standardized test statistic, and so if you remember, we looked at SAT scores of firstborns compared to non-firstborns, and the test statistic was 30.26. The null is 0 because we're saying that there is no difference between firstborn and later-born, and the standard error for the test statistic was 37. The Z statistic, they just simply refer to it as Z. It starts off as the standardized test statistic, sometimes called the Z statistic, and then in shorthand, it'll just be Z. Talk about super confusing. So our Z statistic for our test statistic, and think of that in terms of what's the Z score for our test statistic, is 0.818. And so what we're wanting to do is find the area in the tails beyond the Z statistic for a standard normal distribution. So our Z statistic is what we use to calculate the p-value, to see what's the proportion of values that are as extreme as our test statistic. We'll be using StatKey from now on. So you have mean of 0, standard deviation of 1, that's our standard normal distribution. And then we want to know the proportion of values that are 0.818. And we want to know the proportion of values that are above 0.818. What does that tell us that the p-value for our test statistic is? 0.207. And even if we did it in the unstandardized way, it would provide the same p-value. It's just this is one standard way of doing it. And I did it on this one, and you see 0.207. This is the standardized test statistic, and the p-value is 0.0207. And then if we did it in the unstandardized way, where we create a specific normal distribution where the mean is 0, because that's what the null is, and the standard deviation is 37, and then we said, what are the proportion of values that are above 30.26, because 32.6 is the unstandardized test statistic, and you notice it gives you the same p-value. But in this course, and for future stats, we're going to be using the standardized test statistic, because then you can compare across different test statistics. Standardizing test statistics allows us to assess extremity on a common scale. Again, like it's hard to compare SAT with ACT scores, but if you standardize them, then you can compare them. And so if we standardize all of our test statistics, then we can compare them across one another. The formula for p-value, we have the Z statistic, test statistic minus null value over standard error. So test statistic comes from the observed data. That's our observed sample statistic. The null value comes from our null hypothesis, whatever our hypothesized value would be. And then standard error comes either from our randomization distribution or from our standard error formula. There's two different ways to calculate that. And then obtain the p-value of the Z statistic by assessing its location on the standard normal distribution. And that's what we've been doing. This is how we calculate the p-value for something. So there's not a new formula that you're needing.
So is there a difference between the Z statistic and the p-value?
Yes. So Z statistic is the number of standard errors the test statistic is away from the null.
So that's the bottom number.
Yeah, so in a sense, this is the null value.
Okay.
And then our Z statistic was 0.818, which was 0.818 standard deviations away from the
And
null
your
value.
p-value is telling you like what proportion of statistics fall in that.
Are as extreme as
Okay.
your test statistic, yeah. And then you might say, well, gosh, how do on an exam, we're not going to have a computer. But what I can do, since we will be standardizing all of our test statistics, all I have to do is have this right here with indicators of where the different cut points are. And I could say, given a z statistic for this test statistic is 3, I would say, would we reject the null hypothesis or accept it? If you were told that the z statistic for a particular test statistic was 3, what would be your formal decision? So p-value is proportion of values that are as extreme as, and if our significance level is 0.05, what would we do? Yes, you'd reject the null. You can visually look at it. See, 3 is way out there, and so the p-value is going to be 0.013, and so that's rejecting the null hypothesis. For the homework, make sure you guys grab the assignment. Part 2, I'm going to be basically sending you what the final research project is going to be, and so part 2 of the assignment will be to read it. And then I also am going to attach a list of GSS variables that's in a better format for figuring out which ones you want to use. And then I have a sample paper that's a model or a template, mainly of how to organize your research paper. Make sure you read that, and we'll be talking about it on Monday if you guys have questions about it. And then hand in your homework.